Hello, this is a recording of the 10701 class on Introduction to Machine Learning. Since I'm not around today, I decided to pre-record the class such that you can watch it. Obviously, you should come to class and watch Mansil Sahir explain those things live. But those of you who cannot make it to the class can watch it, of course, online. Okay, so what we're going to do today is cover a fair amount of constraint optimization. So this is basically extending where the TAs left off in the recitations, namely to cover constraint optimization, basic convexity, all those things. Okay. So let's start with very simple convex problems. So the first thing is we should, of course, explain what the convex function is, right? So that was done by the TAs, but in case you're not quite sure anymore what it is, it's actually very, very simple. Suppose I have some function like so. It's convex if all the lines between 2 points on the epigraph majorize the function below, right? So this is a convex function. Likewise, something is a convex set if any 2 points within that set mean that the line connecting those points is also contained within that set. By the way, something is called a cone if the ray going through any point from the origin is also in the set. So think of that like an infinitely sized ice cream cone. And as long as you start a ray from the bottom of the ice cream cone and go through any point within that cone, you will always stay within it. Right? So that's a convex cone. So it's a convex set that's also a cone. Now if I go and take that ice cream cone and push it in on one side, it's still a cone, but it's not convex anymore because I could actually draw a line through. Okay, good. So we've already looked at unconstrained convex optimization problems, and we saw a lot of techniques there, for instance, conjugate gradient, Newton method, and so on. And so today we're going to look at constrained convex optimization problems. So constraints mean simply that I still have the same optimization problem, like minimize f of x, but at the same time, I am going to impose some constraints of the form ci of x less equal than 0. So with those, I can, for instance, constrain a domain in this way. So this might be, for instance, the constraint ci of x less equal than 0. How could I get such a constraint? Well, that's very easy. All I have to do is just take the inner product between x and wi less equal than b, right? Or x dot wi plus b less equal than 0. So that gives me one convex constraint. If I then impose another one, like this one here, the intersection of the corresponding sets will then already give me, so that space. And then if I just continue, I will get that entire set, right? Here's another constraint, and here's another one, and here's another one, right? So that's the overall family of convex optimization problems. One particular thing that I could do is I could look at linear inequality constraints. So those are exactly the ones that we saw above here, like this one there, right? wi.x plus bi less equal than 0. I could also have quadratic cone constraints. So that's something like x transpose qx plus b transpose x less equal than c. So if you write that out, you can see that this actually defines a cone, where this is a positive semi-definite matrix. So for instance, you can impose that to talk about the set of all means and covariances, or rather the set of all first and second order moments of a distribution. And since we all know that these distributions will always have no negative variance, they impose a constraint on the set of means and variances, or rather means first and second order moments. I can also have constraints of the form M positive semi-definite, this constraint here, or I could have constraints of this form like there. So this basically looks like a linear inequality constraint, except that what I'm saying is that the linear combination of a few matrices altogether has to be positive semi-definite. So just a quick refresher, what positive semi-definiteness means, it is that all the eigenvalues of the matrix have to be greater or equal than 0. So this sounds like an insanely complicated constraint. However, it turns out that a large number of problems in control theory can be rewritten as a semi-definite program, and then you can actually solve things optimally that otherwise would not necessarily be so easily solvable. Okay. So this is really just to look a little bit at the zoo of different problems that I could have. Now, just a quick question. Why would equality be a special case of this, right? So after all, we have w.x plus b less equal than 0, and we get something of that form. Well, equality is a special case because, as you can easily see, you can simply have one constraint which says nothing on this side is allowed, and you have another constraint which says nothing on this side is allowed. So the intersection, of course, is exactly that line here. Right. So one example that we saw yesterday, or rather are going to see in the Monday lecture, is support vector machines. So in a support vector machine, remember what we said is that I want to find some parameter vector w and some offset b. So w and b is what I'm really after. And it so turns out that w.x plus b has to be greater or equal than 1 for all observations that are in class 1, and less equal than minus 1 for all those terms, which are negative classes. Okay, so in other words, I actually get that type of constraints. Right. So these are the linear constraints. Furthermore, and we are going to go through this in a little bit more detail in the support vectors part, the objective function will be that I want to have as small a w as possible. So that's this term here. So the norm of w should be as small as possible, and that can be seen as follows. So if I want to have observations that are positive to be classified greater or equal than 1, and those that are negative to be classified less equal than 1, and I want to have a really large margin in between, right? In that case, well, I can always make the margin large enough such that there will be at least one point on one side of the boundary and at least one other point on the other side of the boundary. If that wasn't the case, then I could always just expand the boundary until I go and hit something. Right? So without loss of generality, I'll set the values to 1 and minus 1, and so I get this. w.x1 plus b equals 1, and w.x2 plus b equals minus 1. So taking the difference between those two constraints, which I can do, means that w.x1 minus x2 plus b equals 2. However, what I can now do is I can go and divide by the norm of w, right? And, well, by the way, this is a typo here. This b should not be there, right? So if I now go and divide this entire equation by w, yeah, then I get that this term here has to be equal to 2 over the norm of w. Now, maximizing the margin means maximizing 2 over the norm of w, in other words, minimizing the norm of w, which is the same thing again as minimizing the squared norm of w, which is what we have here. So this is a constrained quadratic program. It's called a quadratic program because I have linear constraints. And I have a quadratic objective function. Now, the obvious question is, how do we actually go and solve this? So the first thing is, you solve it by invoking a quadratic programming solver in MATLAB and Octave or R, or maybe you download one or you buy one. So there are plenty of quadratic solvers that you could actually use. And for small toy problems, that's good enough. And I strongly recommend that you do that for the purpose of rapid prototyping. In other words, it's a really good idea to not bother about detailed implementations if your problem is tiny, and if you just quickly want to see whether your idea is any good at all. As soon as you then go and decide that you actually want to move to a larger scale, you will have to implement it. Right? There's not much that you can do, but basically for small scales, do not go and implement it yourself. Okay. Now, let's actually see how we could solve this. So I'm not sure whether everybody knows what a Lagrange function is. Basically, a Lagrange function is something that allows us to combine objective and constraints into a joint objective and then happily optimize away at it. And that's exactly what we're going to do here. So the Lagrange function is given by, and I'm just going to show you what it is and then we'll actually make sense out of it, is given by f of x, so this is our original objective, plus a sum over constraints. Right. Now those constraints are basically, if they're violated, it means that those constraints, those Ci of x will all be greater than 0. If they are satisfied, they are less than 0. Right? And then I have some Lagrange multipliers alpha, and I'm going to impose that they have to be greater or equal than 0. In other words, what I want to make sure is that I have a penalty alpha that I can impose to make sure that the constraints are properly satisfied, and at the same time, I want to also make sure that I'm solving the original objective function. So basically, minimize f of x while keeping those constraints satisfied. Now, we already saw that Ci of x have to be convex functions. And since sums of convex functions are convex functions, we know that L of x and alpha is convex in x. Right? Furthermore, we know that for any given x, this function here is linear in alpha. Furthermore, what we'll immediately see is that whenever the constraints are violated, right, so whenever the Ci of x are greater than 0, I can make this thing diverge in alpha, right? Because, well, it's linear in alpha, and the alphas have to be greater or equal than 0, and so I can just make it go to infinity. Now what I'm going to do is, I'm going to show that there's actually a saddle point that I can look at, and that basically I'm going to minimize with respect to x, and I'm going to maximize with regard to alpha. And the thing that I'm getting through that, so basically a saddle point, right, that kind of solution. That's what I'm going to, then try and solve. So the key point is that I'm doing various things to turn a constrained optimization problem into an unconstrained one that I can then solve efficiently. And basically, the point is that if there are some x stars and alpha stars, where the alpha stars are non-negative, such that L of x star and alpha is less equal than L of x star and alpha star, less equal than L of x and alpha star, then x star is an optimal solution to the constrained optimization problem. So what basically happens is, let's say this is x star, and here is x, then that part of the constraint here simply says that I can move down this branch. Whereas if this is alpha star, and here is alpha, then, well, this part of the inequality means that the Lagrange function is maximized for alpha star. So I'm pushing up with alpha, pushing down with x, and the combination of those two will actually solve the problem. Right? That's what I'm doing. Okay. So now let's prove that this thing holds. So from the first thing we need to actually check is whether x star satisfies the constraints. So the first inequality, remember, that was this part here, means that, well, x star is the same in both points, so all I have to do is just take the difference between alpha and alpha star. And so therefore, I will actually obtain the fact that, alpha I minus alpha I star, ci of x star, have to be less equal than 0 for all alpha i's. Well, how do you get that? Well, it's actually very simple. What I'm going to do is I'm going to pick alpha equals alpha star for all i's except for 1, and then for I pick, for instance, alpha I equals alpha I star plus 1. And if I do this, I immediately get that ci of x star has to be less equal than 0. And since I could do this for all possible i's, I'm done. So this shows that x star has to be feasible. Furthermore, if I set alpha I equals 0, right? Well, then this follows. Well, why does this have to follow? Because, well, we have the optimality, right? Otherwise, you could improve things. So in other words, I get the condition that alpha I star times ci of x star have to be 0. Right? Because what we have is that, L of x star and alpha have to be less equal than L of x star and alpha star. Now, if I set one of the alphas to 0, it means that, well, yeah, alpha I this has to hold. Okay. So now, what we've just established is that L of x star alpha star has to be equal to f of x star. Right? Okay. Now, we also now know, and this is now the second inequality here, that if I plug in, and this is also, yeah, so if I now plug in the second inequality, this one here, then, well, let's expand it. So this is nothing else than f of x plus the sum over alpha I star ci of x. But what we already know is that these ci's have to be less equal than 0. So I know that, well, basically this has to be less equal than f of x. And so this proves optimality. Because if there were any other x that also satisfies the constraints, right? So that's why I can actually apply the second inequality, because these terms here are less equal than 0. And these here are greater or equal than 0. So therefore, this holds. And so basically what I get from that is that for any other feasible x, I have that inequality. So this proves that things are optimal, not just that all the constraints are satisfied. So we show the constraints are satisfied, we show that the optimization problem is optimal, and everything's good. Okay, good. So now that we've proved this, let's actually check a little bit, under which conditions some of those constraints appear. Because we've just done a fair amount of algebra in public, and the question is, does it actually make sense? So there's 3 different types of constraints, and you can actually look up in a book by Mangasarian. And this is basically somewhere in the 60s, that these constraints are actually all equivalent. So this is stuff that in the 50s and 60s people were doing a fair amount of stuff. The first thing is latest condition, which basically means there exists some x such that for all I, ci of x less than 0. So in other words, it means that there exists a point in that constraint set that doesn't touch any of those boundaries. Right? Remember, if this was my constraint set, it means that there exists at least one point here that does not touch any of those boundaries. So if you remember those other constraints that we had at some point with strict equality, right? There's one, and here's the other one. Those would not satisfy latest condition, because once I'm on this boundary here, I cannot really move around. So the other part is that, well, Cullin's condition, which basically says that for all possible values of Lagrange multipliers, there exists some x such that these conditions are satisfied, which a priori looks like a much weaker condition. Because, of course, if I satisfy this, I get this immediately. And then the last thing is the strict constraint qualification, which is basically, closer to that part up here, which basically means that the feasible region contains at least 2 distinct elements. And, well, that basically have nice strict convexity with that. So these conditions are technical conditions that you may want to check for your constraint optimization problem. Most likely, you will not encounter a lot of pathological cases here in 10701, but you may very well have to check such things once you go and look at more complicated problems, right? So keep in mind that those things exist. You don't really need to do very much with them right now. What is useful, though, however, are the Kuntaka conditions. So those conditions are something that can actually be used to solve optimization problems, which is why I'm going to walk you through them a little bit. So assume that we have some optimization problem that satisfies constraint qualifications and that has a convex differentiable objective and constraints. In other words, let's assume that we have a nice problem. And in that case, the Karash-Kuntaka conditions are necessary and sufficient. So let's actually first look at them. So basically, the saddle point condition in X means that the derivative with regard to L with regard to X of L of X and alpha vanishes. So in other words, dx of f of x star plus sum of alpha I star dx of ci has to vanish. Furthermore, we know that we have to have a saddle point, and that furthermore we have this condition. This was the Karash-Kuntaka condition. Okay, so this is primal feasibility. This is basically the primal optimality part, or in other words, dual feasibility. This is primal feasibility or dual optimality, depends on how you see it. And this is basically what couples those conditions. Interesting aside about the Karash-Kuntaka conditions, so KKT, sometimes people only refer to them as the Kuntaka conditions. The thing is that Mr. Karash was a master's student in, I think, 1934. He wrote in his master's thesis those constraints. And since this was a master's thesis, nobody really read it, and everybody forgot about it. And then about 15 to 20 years later, Mr. Kuhn and Mr. Tucker came up with those same things again. And only later it was discovered that, well, Karash's work predated them by about 2 decades. So that's why I usually refer to them as the KKT conditions. Now let's actually see what can be proven there, because I'm actually going to show you that this condition holds. So the first part that we're going to exploit is that since I have a convex function, f of x minus f of x star have to be greater or equal than this condition here. Well, you can see that immediately just from this, and you can see that the linear extrapolation has to be less equal than the difference, right? Which is basically what we have here, right? So if I apply a tangent at this point, then, well, this tangent is going to be a lower bound on the function. So that's why this condition here holds, this first condition. Right. Now, since we have a saddle point in x star, I can replace this just by the first order conditions because I know exactly what that derivative is like, right? So I know that dx of f of x star has to be the same as alpha I star dx of ci of x star. Just recall what we had was that, f of x plus sum over I alpha I ci of x. Now at optimality, of course, those two pieces have to balance out, and that's exactly what happens there, right? So then I'm going to apply convexity again, this time on the CIs. So it's exactly the same argument as what we made here, just in the other direction. So again, this is greater or equal than minus sum over I alpha I star ci of x minus ci of x star. And then, since I know that, this is basically greater, that since I know that alpha I star ci of x star has to be 0, so basically that means that this term here can be eliminated, and all I'm left with is this here. And so now I know that this has to be greater or equal than 0, and I'm done. And I screwed up a sign somewhere, so we would have that one here. Right. And so basically what I'm showing now is that for any x other than x star, this inequality has to be greater than 0. And so therefore, I know that these are actually necessary conditions. Okay. So that was a large amount of math just to explain to you constrained convex optimization. I know that this isn't easy, and I just want to make sure that you have a bit of the background of how those problems work and why you use them, rather than just invoking them like cookbook recipes. If you got lost in this part, don't worry. It turns out that for the rest of the understanding of support vector machines, you only need operational knowledge of those constraints. But if you actually want to go and design new and large systems on your own, it's probably a good idea to have a little bit more than just operational knowledge and actually be able to design those things on your own. Okay. So now we're going to move on to linear and quadratic programs. So linear programs are about the simplest thing that you can imagine. And there's actually a nice example where people used linear programs to, well, for instance, optimize food for soldiers. So I don't know whether any of you have been in the army, but basically army food usually has the reputation of being really horrible, right? And maybe there's a reason for it, right? And it actually turns out that, at least based on one approach of how to compose a menu, yeah, there was a pretty good reason why it's horrible. And I'm going to show you why. So suppose that, I have, for each food item, let's say here's an egg, and this egg, okay, it's not a 0, it's an egg, right? This egg has a certain amount of protein and fat and carbohydrates. It has a lot of protein, maybe it has 3 units of protein, 1 unit of fat, and maybe 1 unit of carbohydrates. And then maybe an apple, which is now going to look exactly like the, well, it looks a bit different from the egg. It maybe has no protein, it has no fat, and maybe it has some carbohydrate units, and so on and so on. So you basically get a large matrix here. Let's call this matrix here A. And I want to go and feed the soldiers, right? So basically I need to decide what I'm going to buy. So this is not a made-up example. This is actually what the US Army used in the 50s. I hope they don't use it today anymore. So what you basically do is you want to find out, which things you want to buy. So X is my shopping list. And I want to buy things in such a way that the soldiers will get enough protein, enough fat, and enough carbohydrates. So I want to make sure that they get a balanced diet. So what I'm going to do is I'm going to require that A times X has to be greater or equal than some diet. And basically, let's say D bar. And of course I can bring that over on the left-hand side and flip all of those things with a negative sign, right? And then I will actually get exactly this constraint here, AX plus D less equal than 0, after flipping things accordingly. So basically, that constraint just tells me, well, don't starve the soldiers. Now at the same time, I want to save money. So there's a cost associated with each item. Maybe eggs are a lot cheaper than apples. And you basically want to minimize the cost of the shopping basket. And of course, you also want to make sure that you don't buy negative amounts of items, because you cannot extract eggs from soldiers because they're not chickens. So you would probably have something of the form, xi greater or equal than 0. And so that's an additional set of constraints. And you have costs. Right. So I want to minimize the overall cost under the constraint that I cannot extract food from soldiers and that I need to nourish them well. Then you optimize. So if the prices change, then maybe you change your diet. But that basically means that now being a cook has absolutely nothing to do with what you're going to feed them. This is maybe being a nutritionist, that's what this is called. Anyway, so joke aside, a linear objective under a lot of linear constraints, or in other ways, well, combining all of that into a matrix, namely a matrix A times X plus D less equal than 0, that's really how you solve the problem. Now if we do this, and we want to make sure that we get the Lagrange function, then, well, all we have to do is just move this term over here and move this term over there, and we're done with writing out the Lagrange function. Now, optimality conditions just mean that the derivatives with regard to x and alpha have to vanish. And so if I take the derivative with regard to x, I basically just get c plus a transposed alpha equals 0, right? That's basically this term. And if I take the derivative with regard to alpha, I get, well, lo and behold, the original constraint back. Right. Well, we didn't really gain much, but, well, we'll see in a moment. And then I can therefore, use this to get 0 equals alpha transposed ax plus d, because I can always, plug that back in. And then I get, furthermore, the optimality conditions that the alphas have to be greater or equal than 0. That's basically dual feasibility. Now, if I do this, I can actually plug this condition back into the Lagrange function, right? So this first condition here means that I can eliminate something from the problem. Namely, I can eliminate anything that contains x. So it's exactly this green part here that I can remove from the objective. And so what I'm left with is d transposed alpha, or alpha transposed d, if you will, this part here, under the constraint that alpha a transposed alpha plus c equals 0. It's this constraint here. And that furthermore, that the alphas have to be greater or equal than 0. Right? So what we just saw is that it's fairly straightforward. By just plugging those first order conditions into the Lagrange function, I can eliminate the primal variables, so I can eliminate the x's, and I get the problem that's now just expressed in terms of the alpha. And lo and behold, this is again a linear program. This is actually called the dual linear program. Now sometimes this can be a lot easier to solve. For instance, imagine that x was very, very high dimensional, right? If x is very, very high dimensional, then I have a lot of variables to deal with, and that's maybe really bad. And then maybe in the dual problem, d transpose alpha, maybe, this is a very small number of variables, maybe I have only 2 or 3. But the problem is that I'm now going to have a large number of constraints. And those constraints can make my life miserable. Okay. So it really depends on whether the primal or the dual problem is easier to solve, which one you pick. Right? That's exactly what we did. So another interesting thing that is going to be kind of a common theme is free variables become equality constraints. Equality constraints become free variables. Inequalities become inequalities. And the dual of the dual is the primal. I'm not going to prove the last thing for you. This is something where you can just go and sit down and apply dualization again to this. And then you get the primal objective out of it. Now, here's the interesting thing. Free variables become equality constraints. Where did we see this before? Well, we saw that when we had an unconstrained optimization problem. Let's say I want to minimize over x, f of x. The first order condition is that dx of f of x equals 0. Right? If I have an unconstrained problem, that's the only thing I need to know in order to find x. So what I'm now doing is I'm solving an equality constraint in order to find the optimal solution. Well, that's exactly what you would expect to do if you had an unconstrained problem, or likewise if you have a constrained problem where you have this variable and a whole bunch of other stuff. And it turns out that, of course, if you use the other way around, if you have an equality constraint, so this is the one thing that I didn't really talk about very much yet, but it's very easy to show that if I don't have something like ci of x less equal than 0, but maybe I have ci of x equals 0, then in this case, I basically just take alpha I times this, and I use this in my optimization problem, right? So that's basically where you can see that an equality constraint will lead to a dual free variable. So where this dual free variable here are the alphas. And inequalities will just turn into inequalities, but the dimensionality may change. Okay. And all of this is useful because sometimes you have a really inconvenient primal problem, and then by switching into the dual it's easy, and so on. You can play exactly the same game for quadratic programs. So in the quadratic program, I have a very simple objective. I have basically just a quadratic function as the objective, and the constraints look exactly the same. Now we're going to play exactly the same game as before. We're going to take the quadratic objective, this one here, and we're going to add to that all the constraints and add it up, and then, lo and behold, we get the Lagrange function. So this is exactly the same thing as what we did before, just that now the function looks a bit different. Then we take the first derivative with regard to x and alpha. So those are those two operations here. And they will lead to an equality constraint in x and another inequality constraint here. Well, this one actually just so happens to be exactly that one here. Right? And then, by just plugging this back in, I get that 0 equals, this is the Contact condition, alpha transpose ax plus d. And, well, I basically have this because I introduced Lagrange multipliers. Okay. So now let's actually plug this back in. So, right, I can solve for x. So let's do that. So I get that x equals q inverse with a minus here, a transposed alpha plus c. And now I'm going to plug this x back into the Lagrange function. Here. Why can I do this? Because I know that this is the optimal x in the Lagrange function, and what I want to do is I want to make L a function of alpha only. Okay. So when I do this, after a fair amount of work, I will get this as my dual constraint. Okay. So now this term depends only on alpha, and again it's a quadratic objective. This is a constant, this is linear, and this is quadratic. And I have some additional constraints. So when you deal with a support vector optimization problem, you almost invariably are going to make exactly that operation to go from the space of parameters that may live in an infinite dimensional space into an optimization problem that lives in a finite dimensional space and therefore can be solved efficiently. Okay. So, to look at the problem again, it's exactly the same as before. With a primal problem, we have a different dual, which may or may not be simpler. Well, when the dual constraints are simpler, maybe then this is good. I may have fewer variables. Now, an interesting thing here happens is that the dual of the dual problem is not always the primal. Well, why is that the case? Because I started out with an optimization problem in an infinite dimensional space. And so, since that happened, in the dual, I actually collapsed some things out where I only express things in terms of inner products. And so that's why I cannot get the original problem back. That's basically one of the main reasons why sometimes people derive the dual of an SVM and then dualize it again to solve efficiently. But that's something for another time. So I want to show you now is how you can actually solve those things efficiently. So these things are called interior point methods. So the first thing I want to do is I want to show you what happens if you have a convex objective and a linear constraint. And the reason for that is because that's kind of the simplest case of a constraint optimization problem, where I'm saying, well, I have a nice convex function, but I'm actually constraining myself onto a subspace, named the subspace of ax plus equals b, and then within that space I can solve. Okay, so this is an affine subspace. So the Lagrange function and optimality conditions are just as what we had before. Dx of f of x plus a transpose alpha equals 0, and ax minus b equals 0. Okay. So if you squint at that and you aren't very careful, you might wonder, after all I have ax equals b, and I have this constraint here, can't I just go and say x equals a inverse b? Well, why is that a bad idea? Well, it's a bad idea because at this point I then actually will end up with something that is underdetermined. Because A may be, for instance, a short and fat matrix of that form. If that is A, then A cannot be inverted. It only gives me a subspace, and so that doesn't help. Now remember when we looked at the Newton method, right? In the Newton method, what we did is we said, well, let's just obtain a second-order Taylor expansion of my objective and then see what I can do. And this is exactly what I'm doing here. I'm going to make a Taylor expansion of the gradient, or in other words, a second-order expansion of the objective itself. And that means that dx of f, right, this equals dx of f naught plus and then a linear term plus some higher order terms. Now this gets plugged back in here. Okay. And so now I end up with two sets of constraints. So I have some constraints, namely second derivative in x of f, and a transposed times x times and alpha is this thing here. And then I get another constraint just in the a's as what I had before. So basically this thing here. Okay. Now this is a problem that is now fully determined, and now I can go and happily solve it. Whereas before I had something that was underdetermined. Okay. Now, this is a particularly nice thing if I have a constraint optimization problem, you really don't need any interior point solver or whatever, and you can just happily go away and solve it. The general strategy for an interior point solver, which is basically this but on steroids, is that I have those optimality conditions and I have a Kuntake condition. So what I'll do is I'll solve these optimality conditions repeatedly, and then I therefore am going to reduce the amount of infeasibility in the primal set. So that's basically these conditions here, and in the dual, which are these conditions here. And at the same time, I'm going to make sure that my primal and my dual objective get really close. This is basically moving along the saddle point. Now, why is this really nice? Because at the same time, I can measure, is there actually a feasible solution? And furthermore, I'm going to get an upper and a lower bound on the objective. So, a couple of interesting things. I don't need to impose feasibility at the start, which sounds weird because it's an interior point method, so you would think that basically you move along the set that is always feasible, and the original problems actually required this. So they would, for instance, have something called a barrier function, which made sure that you never left the region of feasibility. But if you have a primal dual problem or a primal dual approach, this is actually not necessary. There's a lot of really nice work by a guy called Rob Vanderby. I think he's still in Princeton. And you can look up his papers on that. So let's have a look at what happens in quadratic programs. The reason why I'm going through this in detail is because these are exactly the problems that you're going to encounter when you solve a support vector machine learning problem. So we have optimality conditions, right? So we have basically, because we started out with 1/2 x transposed qx plus c transposed x. This was our objective, plus some constant. And so taking the derivative of this will give me exactly qx and c. And the optimality and the constraint, namely, ax plus b less equal than c would give me a transposed alpha. Likewise, I get the dual constraints. I'm doing this here, and then I get the Constraint conditions. So since it's really hard to solve the product of two variables being 0, because it basically just means if alpha equals 0, then psi is not 0, and if psi is 0, then alpha need not be 0. So what I'm going to do is I'm going to relax this. Then I solve a linearization of this nonlinear system, and I iterate until converged. There's one really useful detail that you should keep in mind whenever you solve quadratic programs, or overall when you solve quadratic systems. This is called a predictor-corrector approach. So basically what you do is you take some function f of x, and I want to minimize this. So I go and compute some delta x, and I see what happens at f of x plus delta x. And most likely I would have overshot or undershot or somehow slightly made things wrong. What I then do is I go and add the first order changes of the problem into the original optimization, into the original linearization, and then I resolve again. And as it turns out, you can check that algebraically, this gets rid of the first order terms, so you only are left with second order error terms. So predictor corrector is an extremely useful technique for making sure that I get essentially second order conversions without really having to compute a lot of second order derivatives or inverting lots of matrices. So this is an extremely useful trick. It doesn't only apply to convex optimization. So remember this trick whenever you have an optimization problem. So then, you might wonder, how much of a mess is this? Actually, in MATLAB, it's maybe one screen of code, which is kind of nice given that convex programming solvers, so like quadratic programming solvers, tend to sell for many thousands of dollars. So it's kind of nice if within one screen of well-written MATLAB or Octave, you can match quite often the performance of a dense general purpose solver on certain problems. So what you do is basically you go and solve the optimization problem, you take an update step, you make sure that you do not actually, become infeasible in the slack variables, and then you just update this again. So and usually after about 20 iterations, you're done. So there are pointers to a lot more details on how to implement that in practice at the end, and it's actually fairly straightforward. So here's some links to some solver software. I can very much recommend you to look at this, at the object-oriented quadratic programming solver. The object orientation in this case is that, well, if I have a quadratic program, I need to perform a matrix vector product, and at some point a vector-vector product, and at some point I'll have a constraint. Now, in many practical cases, these matrices will have very, very special structure because of the specific engineering problem that you're going to solve. And so it makes a lot of sense for you to actually exploit this and then just plug it in. This way, you can be much faster than off-the-shelf solvers. Parallelizing that is not always easy unless you go and parallelize at the level of the linear algebra routines. So one thing that I want to go into a bit more detail is bundle methods, which are really useful if you have a convex optimization problem that is really large and messy and you want to efficiently deal with that. So this occurs in many practical cases. So for instance, in density estimation, we actually had this. So remember, in exponential families, in exponential families, you had exactly the log partition function and the linear term. And you wanted to optimize over that. And let's say you impose some quadratic regularizer. Or in penalized regression, so remember the least mean squares regression problem that we had in homework 2. That's basically that form. So the question is, can you actually deal with that efficiently? And the problem is really that the sample size M is absolutely gigantic. And so how can we do this efficiently without really paying all for that? And the basic idea is actually very simple. And this applies to a lot of problems, and people have used special instances of that quite a lot. But here's the idea. So this convex loss, the sum over loss functions here, is really expensive to compute. Right? So in other words, if we at some point look at that and compute this gradient, just do something interesting with it, we better make the most out of it that we can. Right? Because, well, we worked so hard to get it. On the other hand, that, regularizer, basically the thing that we use to keep our model simple, is convex and cheap to compute and to solve. Another thing is that on this loss function, whether I go and compute just its value or compute its gradient, it doesn't cost me that much more. And on top of that, it can be very nicely parallelized, because what I simply do is I break the sum up into a sum over instances and a sum over machines. Right? And so that way, I can just use, for instance, MapReduce to get those gradients, aggregate, and get done. Now, exploiting those two things, it's very clear that if I ever get a gradient, I better make as good use of it as I can. So in other words, if I can reuse it more than once, I should do that. So the strategy is basically to go and compute tangents on the loss function. And then, well, they obviously give me, since it's convex, a lower bound on the objective. And then, I go and solve that lower bound, and I keep on iterating. So let's actually have a look at what this looks like in practice. So this is what's called a bundle method, and I'm probably going to skip over the technical details of how exactly it works, but I just want to convey the overall idea to you. So if this is my empirical risk, and this is amazingly expensive to compute, right? So then, if I compute its gradient, at some point I want to make good use of it even afterwards. Furthermore, I can see that each of those is going to be a lower bound on the objective. So why not actually take the maximum of those things, and then I get something that's actually not such a horrible bound on the problem, right? So this green function is a piecewise linear function that is actually not so terrible if I want to go and, get the lower bound on my objective. What it also means is that if I ever go and solve that lower bound, and maybe I end up here with a solution, right? Then I can go and compute that value, and it tells me that at the very most I am that far away from optimality, right? Because I've minimized a lower bound. And so by going up here, I know that this true function has to be always greater or equal than that, and since this is a current lower bound, I know that this gives me a guarantee on the quality of the solution. And so I do exactly that. I go and compute a Taylor approximation, and I get basically that this is the bound for the empirical risk, and then the regularizer just stabilizes the problem. And that is very simple to solve. It's basically compute the gradient, solve a much smaller quadratic program, and then compute a new gradient. And the good thing is that at each step, I know an upper bound and I know a lower bound, so I know exactly how close I am to optimality. It's this thing here. Okay, now the dual problem is also really easy. And since I have a small number of constraints, I will actually get only a small number of variables. And it turns out that actually solving this is very cheap. Okay, I'm not going to go into a lot of detail here, except that, yes, this can be done very nicely map reduce. This is basically map. This is reduce. And this is a small update. So as long as I don't care about the fact that while the reducers are doing their job, or in particular while the bundle solver is doing its job, that the mappers are idle, I can actually do a good job. So this is probably, within a factor of 2 or 3 of, what a much more efficient algorithm could do that actually does everything asynchronously. But if I just want to have an idiot-proof simple system, then this is not too bad. I can actually get decent rates, and I'm not going to walk you through the details of the proof. Okay, so this brings us to the end of the constrained convex optimization. Next time, we're going to look at online methods and then at discrete programs and so on, but I figured this is probably as much math as what you wanted to have. This was fairly intense.